In this episode, we're going to talk about feature engineering in a way that feels practical and safe for beginners. Because the phrase feature engineering can sound like a secret art when it is really a disciplined way of turning raw data into signals a model can learn from. A feature is just an input you give the model, and feature engineering is the act of shaping those inputs so they represent meaningful patterns instead of awkward, misleading numbers. The goal is not to trick the model or inflate performance. The goal is to help the model see what matters in the real world. Scaling, binning, interactions, and domain ratios are four common tools for doing that, and each one solves a different problem. Scaling helps when features live on very different numeric ranges. Binning helps when fine-grained numbers hide simpler patterns. Interactions help when the relationship depends on combinations. And domain ratios help when relative comparisons are more meaningful than raw counts. If you can understand why these tools work and when they can backfire, you will engineer features that add clarity instead of noise. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Scaling is a great place to begin because it addresses a basic issue. Many models learn more easily when input features have comparable numeric magnitudes. If one feature ranges from 0 to 1 and another ranges from 0 to 1 million, the larger feature can dominate certain training processes even if it is not more important. Scaling is the process of changing the numeric representation without changing the underlying information so that the model can consider features on a more balanced footing. Two common forms are normalization, which often maps values into a fixed range like 0 to 1, and standardization, which often centers values around 0 and scales them based on spread. You do not need to memorize the formulas to understand the intent. Scaling is about making the step sizes in learning feel sensible across features. It is especially important in models that use distance or gradient-based optimization, because those methods can be sensitive to feature scale. Scaling can also improve interpretability and stability, but it is not always necessary, which is an important nuance for beginners. Some model families, especially mini-tree-based approaches, are less sensitive to scaling because they split on thresholds rather than using distances directly. However, even when scaling does not change performance dramatically, it can still be useful for comparing coefficients in linear models or for making training more stable in neural networks. A common beginner error is to scale everything automatically without considering feature meaning, especially with features that are already in a meaningful bounded range. Another error is to scale using information from the entire dataset, including data you should treat as future or held out, which can subtly leak information. The safe mental model is that scaling should be learned from the training data context and then applied consistently, so the model never gets a peek at values it would not know in the real world. Thinking this way keeps scaling in the category of helpful preparation rather than accidental cheating. Binning is the next tool, and it is best understood as turning a continuous range into a small number of meaningful buckets. Beginners sometimes assume that more numeric precision is always better, but real-world measurement often contains noise, and models can overreact to tiny differences that do not matter. For example, an age of 31.9 and 32.1 might be effectively the same for a business decision, or a response time difference of a few milliseconds might be irrelevant compared to the difference between a typical response and a timeout. Binning can reduce sensitivity to irrelevant tiny changes and can help capture nonlinear patterns, like a risk that jumps after a threshold rather than increasing smoothly. It can also make a feature easier to interpret because bins can correspond to categories like low, medium, and high ranges. The key is that binning trades detail for robustness, and that can be a good deal when the detail is mostly noise. Binning can be done in different ways, and the choice reflects what you believe about the data. Equal width bins divide the numeric range into evenly sized intervals, which is simple but can produce bins with very different numbers of data points if the distribution is skewed. Equal frequency bins, sometimes called quantile bins, aim to put similar numbers of observations into each bin, which can make learning easier but can also group together values that are far apart numerically. Domain-informed bins use meaningful thresholds, like a known performance standard or a policy boundary, and these can be the most interpretable when you have that context. A common misconception is that binning is only for visualization, but it can be a powerful modeling tool when relationships are not smooth. The risk is overbinning, where you create too many bins and end up with sparse categories, or underbinning, where you hide important structure. Intentful binning is about capturing the simplest structure that matches the decision context. Interactions are where feature engineering starts to feel like you are modeling relationships rather than just preparing columns. And that is often where beginners get excited and also where they can go wrong. An interaction feature represents a combination of two or more features, designed to capture the idea that the effect of one feature depends on the level of another. For example, a high number of failed logins might be more suspicious if it happens from a new device, and less suspicious if it happens from a known device during a password reset. The model might be able to learn this pattern automatically, but adding an interaction can make it easier, especially in simpler models that assume additive effects. Interactions can also capture ratios or differences that reflect meaningful contrasts, like the gap between planned and actual time. The key beginner lesson is that some patterns live in relationships between variables, not in single variables alone. The danger with interactions is that you can create a huge number of them, and many will be meaningless or will overfit, especially with limited data. If you combine many features, the feature space can grow quickly, and that can create sparsity and multicollinearity issues. Another subtle risk is that an interaction can accidentally capture leakage, such as combining a pre-event feature with a post-event feature that should not be available at prediction time. To use interactions responsibly, you should think about the story you believe could be true in the real world and create interaction features that express that story. In other words, you should not generate interactions just because you can. You should generate them because you have a reason to believe the combination is meaningful. When done well, interactions can help simple models approximate more complex relationships without becoming tool-specific or overly complicated. Domain ratios are one of the most consistently useful forms of feature engineering because they encode relative relationships that are often more meaningful than absolute counts. A ratio compares one quantity to another, such as errors per request, spend per customer, bytes per session, or late payments per month of tenure. The power of ratios is that they normalize for scale differences between subjects, making behavior comparable across entities of different sizes. For example, 10 errors might be alarming for a service that handles 100 requests, but it might be normal for a service that handles 1,000,000 requests. The ratio errors per request captures that context, while the raw error count does not. Ratios also help capture efficiency, intensity, and concentration, which are concepts that appear across many domains. For beginners, ratios are a bridge between raw data and meaningful human interpretation. Ratios come with their own safety concerns, especially around division by small numbers or zeros. If the denominator can be 0 or near 0, ratios can explode into extreme values that dominate the model and distort learning. This is not a reason to avoid ratios. It is a reason to define them carefully and consider whether to cap extremes or use smoothing ideas that prevent infinite values. Another risk is that ratios can hide the magnitude of the numerator, meaning the same ratio can represent very different absolute situations. For example, 1 error out of 1 request and 1,000 errors out of 1,000,000 requests both give the same ratio, but the operational significance might differ. A good approach is to consider using both the ratio and the raw scale feature, so the model can learn intensity and magnitude together. The deeper point is that domain ratios encode context, but you still need to respect edge cases and interpret what the ratio really represents. Scaling, binning, interactions, and domain ratios also connect to each other, and understanding those connections helps you engineer features that stay consistent and reliable. Scaling can make interaction terms behave more predictably because multiplying two scaled values produces numbers in a manageable range. Binning can convert a continuous variable into a category that interacts naturally with other features, like a high-risk bucket interacting with a device type. Ratios often benefit from log transforms or scaling because ratio distributions can be skewed, with many small values and a few large ones. If you engineer features without considering their distribution shapes, You can introduce heavy tails and outliers that destabilize learning. Feature engineering is not just about creating new columns. It is about creating columns that behave well statistically and make sense conceptually. This is why EDA habits and feature engineering habits should be treated as one continuous workflow rather than separate stages. A beginner-friendly rule is that every engineered feature should answer a simple question you can say out loud in plain language. Scaling answers: how can we compare features fairly in learning? Binning answers: can we capture a threshold or simplify noisy precision into meaningful ranges? Interactions answer: does the effect of one feature depend on another feature? Ratios answer: is intensity or efficiency more meaningful than raw volume? If you cannot explain what the feature means, you probably should not create it yet, because you will not be able to debug it or defend it later. This is also how you avoid creating features that leak target information or encode unintended bias. When you can explain the feature, you can also check whether it would be known at prediction time, whether it could be manipulated, and whether it reflects a stable relationship in the real world. By the end of this topic, you should see feature engineering as a careful act of translation from messy measurements into signals that align with how people and systems behave. Scaling helps your model learn from features fairly by managing numeric magnitude and stabilizing learning. Binning helps you capture meaningful thresholds and reduce the noise of overly precise numbers when the decision context is simpler than the raw measurement. Interactions help represent relationships where combinations matter more than single variables, especially when effects depend on context. Domain ratios help express intensity and relative behavior, making comparisons fair across entities with different scales, while still requiring careful handling of zeros and extremes. When you use these tools intentionally, you build features that help the model learn real patterns instead of memorizing quirks, and that is one of the most important skills for building trustworthy data AI solutions.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.